Okay, good evening, everyone. Um, so I apologize again for the last minute cancellation of our last meeting. It was that's true, Jerain, and I'm pretty sure everybody else will tell you that also. I'm a hard person to reach via email, but I was responding to my emails yesterday. I did email a bunch of people back, and I was going through some grading things, and I got a lot of stuff out of the way. I said it in the other class. I'm pretty sure it's on the recording. If you didn't watch it, I'll say it here again just in case. I noticed as I was grading some of the discussions that people for their original posts were pretty much straight up plagiarizing things off the internet. I am aware when people do that. I can tell when something is plagiarized. So I quickly find the source and I link it to the rubric and I give you a 0 for it, which I did for some people. And I'm not saying who, and I'm not saying if there's somebody that's in the meeting right now, but I did it for a couple of people and it was not enjoyable for me to do, but I did it. And I will continue to do it if people continue to plagiarize. So don't plagiarize. In any case, I extended the due date of the lab for the black body radiation. For some reason, it defaulted to being due at 10 a.m. and not 11:59 p.m. on Sunday evening. And I don't know what people's schedules are like. I don't know how many people waited until the evening of Sunday to do it before the deadline. So given that I don't know what your work weeks typically look like, I extended the due date to next Sunday, May 9th. So that will be due then. There was another discussion post that I saw not a lot of people answered. It was the one where it said that I would assign you a planet, and I'm sorry that I had dropped the ball on that. I didn't realize it was that week. So I extended the week 6 discussion post. If you did not do it because you did not have a planet assigned to you, planets were assigned on Blackboard last night by last names, right? So depending on what the first letter of your last name is, will dictate what planet you are assigned.
Wait, I have a question.
Yes,
I'm
sure.
so sorry to cut you off, but I was like afraid not to do it, so I ended up doing it. So
yeah, I saw people do that also. If you already posted, you don't have to change a thing. All right, you don't have to change a thing. If you don't mind me asking, which planet did you choose?
I chose Neptune.
Awesome. I think I was just worried that a lot of people were just going to choose Earth if I didn't assign it, and then everybody would be commenting on the same planets, and that just wouldn't have been any fun. All right, so so in any case, if you already did it, nothing to worry about. If you didn't do it yet, I assigned a planet to you by the first letter of your last name. But yeah, last Monday rolled around and I was just so beat because I had gotten married 2 days before and it was an exhausting weekend. And so I just needed to recuperate, and everything that happened on Monday was just like, I'm not doing it. I couldn't do it. So thank you very much.
Congratulations.
Thank you. And so here we are 2 weeks later. And we have some stuff to catch up on. So I'm going to, I don't know, did anybody here get to watch the video from the earlier class? You may have seen that underneath the embedded video on Blackboard, I gave a link where you'll find an episode of Cosmos, which we watched as a class earlier.
I watched it.
Great, that's amazing. For those of you that didn't watch it, you should watch it. It's a really good video. It led to a lot of just great discussion about greenhouse gas emissions and how it affects us on Earth, in the United States, in our homes. So please, please, please go ahead, watch it. I highly encourage that you do that. I'm going to show you 2 slides that I didn't get to finish with in the earlier class, and then we'll move on to what I wanted to discuss this evening. Okay, so starting in, it was around 1957, there was a scientist whose name was David Keeling. David Keeling worked for the Scripps Institution of Oceanography, and he was located in Hawaii, near Mauna Loa, which is a large volcano on the Hawaiian Islands. And at that location, they had these monitors to track the amount of carbon dioxide concentration, or not, to track the amount of carbon dioxide in the atmosphere. And these sensors have been working nonstop ever since to track carbon dioxide concentration measured in parts per million, which is typically how we report CO2 levels. And you can see here that there is a pretty much steady, well, it doesn't look quite linear. It actually looks like it sort of curves up a bit, because it is curving up. Trend line, right? So there's this sort of like exponential trend line that we're seeing here, as it relates to carbon dioxide concentrations in our atmosphere. And this is a graph similar to what you'd find anywhere on Earth that you are measuring carbon dioxide in the atmosphere. Right, you'd see this uptick. But you'll also notice if you zoom in on any given year, right, every tick mark on the bottom on the horizontal axis represents 1 year's worth of time. You'll notice that the graph basically like spikes and comes back down. It's like a bunch of little saw teeth, right? Again, it's just all the way up. And I'm wondering if anybody could, put into words why this curve is not just a straight line. Right? Why do we not just see a straight line concentration rise of CO2? Why is it like a sawtooth pattern? Anybody think that they have an answer for that? You can say that you're not sure, but give me something. I will take your silence as your response. We do not know. So if you look carefully, what you'll find is that the amount of carbon dioxide in the atmosphere corresponds with the seasons. On the Earth's surface, there are all of these different types of landscapes. There are dry, arid deserts. There are icy tundras, rocky, mountainous regions, and then we have lush forests, right? Forests that are, we have evergreen forests. We have the Amazon. We have, bunch of forests. But what a lot of people don't know is that most of the world's forests are in the northern hemisphere. And trees are what take in carbon dioxide and basically convert it into oxygen, which then gets released and makes our air breathable for us. Now, in the summertime of the northern hemisphere, in the spring and the southern and the summertime, those trees have leaves on them, right? They're in full, everything's in full bloom in the spring and summer, which means that carbon dioxide levels are pretty low by comparison to the rest of the year, right? Because there are a lot more trees that can take in carbon dioxide. And then in the fall and in the winter time in the northern hemisphere, because again, that would be spring and summer for the southern hemisphere. So in the northern hemisphere, fall and winter, we have trees that lose their leaves and lose their ability to take in carbon dioxide and emit oxygen. Right? And so that is essentially what the Keeling curve is showing, right? It's showing that natural breathing of the Earth's trees, right? Taking in carbon dioxide and releasing carbon dioxide as the trees come in and out of season. And so, to summarize everything that was discussed earlier this afternoon, how does Earth's atmosphere affect the planet? Well, one, it erodes Earth's surface, right? It's the existence of an atmosphere that allows for weather and erosion. Our atmosphere protects us from radiation like ultraviolet light, right? We have the ozone layer to thank for that. And it also traps heat. And one of the main points that I want to convey is that trapping heat isn't a bad thing. Trapping too much heat is a bad thing, right? If the Earth didn't trap any heat at all, right? If our atmosphere could not retain heat, we'd be living in an icy snowball, right? It just wouldn't be warm enough to have liquid water at the surface. So it's the fact that we have some carbon dioxide and methane and other greenhouse gases in our atmosphere that allow the global surface temperatures to be warm enough for life to thrive. And so we want to make sure that we don't tip the scales too much towards an overabundance of greenhouse gases that would really make it unbearable to live on Earth. Okay, so now I'm going to pull up our next part of the lecture. Here we go. We're going to start to compare the atmospheres of the different planets. Okay, so by the time we're done with this set of slides, we want to have an understanding of, why are the atmospheres of the terrestrial planets different? What else is there to know about the Jovian planets in terms of their composition and weather on those planets? Do they even have weather on Jupiter? What about the moons of these large gas giants? What makes them, I guess, interesting and different than other things that you might find in the solar system? And we'll explore some of their geological activity. So let's talk about Venus for a second, right? Venusian geological activity. Right. Well, we know that on Venus's surface, there are craters. We know that there are volcanoes, and we also know that there is tectonic activity. Right, tectonic activity is often what we on Earth, when we're talking about tectonic activity, we're talking about like the movement of these large masses called tectonic plates, which allow for mountain building and sort of a restructuring of, or rather, I don't want to say a restructuring. I feel like that's not the correct word there. They allow for a constant or a continuous makeover of Earth's surface, right? So like continents move around the current location of continents is not what they were 250 million years ago, or 300 whatever million years ago when like Pennsylvania was on the equator. You know, it's like things are always moving around. Tectonic plates collide, mountains are built, tectonic plates spread apart, new oceans are created. Right? But on Venus, it's a little bit different, right? Because the surface of Venus is very hot, and this is something that we discussed in the earlier section. That Venus is a planet that has experienced a runaway greenhouse effect, right? The composition of Venus and Earth's early atmospheres were very, very similar, but the two planets turned out so vastly different. One is an oasis of life, and one is a hellhole. And if you're wondering why, it's because Venus was that much closer to the sun that it didn't really have oceans or an ocean to absorb the amount of carbon dioxide in Venus's atmosphere. Right? So on Earth, there is an ocean and carbon dioxide, and Earth's oceans were able to absorb that carbon dioxide and sort of like sequester it, you know, remove it from the atmosphere. And that prevents that, you know, the fact that it's being stored in the oceans makes it less hot. Where on Venus, there were no oceans. And so it just got hotter and hotter and hotter the more greenhouse gases entered the atmosphere from within the planet's surface. In any case, so Venus is incredibly hot, and because it has such thick greenhouse gases, it's almost like a smog, right? It's just smog everywhere, and you don't have fast winds on Venus because the air is so heavy, right? It's so thick, and because it's so hot, that also changes how the surface behaves, right? The tectonic activity that we see on Earth, you know, if you look over Earth's entire surface area, there are like 17 major tectonic plates and maybe some tiny ones, maybe. But on Venus, there are thousands of tectonic plates, if we can even call them that. Maybe they're not quite plates, they're just tectonic stresses. And that's because the planet is so hot, right, that the crust doesn't behave the same way that Earth's crust does, right? It has to do with like how the crust melts and how thick the crust is. So we have a different kind of activity going on there. All right. So now to just spend a little bit more time reiterating the runaway greenhouse gas effect on Venus. You know, there's this very thick atmosphere made of mostly carbon dioxide. You know, there is no ocean to store all that carbon, and so it just sits there in the atmosphere, keeping Venus hot, making it difficult to see the surface. And on Earth, we are, you know, we do not have to worry about that same fate, or at least we haven't had to worry about that same fate, because we have an ocean that can store the carbon that's in the atmosphere. All right, so to summarize a little bit about Venus, Venus is geologically active, right? It is the planet itself, and I'm not talking about the atmosphere, but the planet itself is hot enough to have geological activity. You know, we know that there's volcanic activity at the surface. We know that there's tectonic activity. There are Venus quakes. Now, when we think of geological activity, we also tend to think of this like larger plate tectonics, and you don't really have that on Venus. Nor do we really see much erosion because the atmosphere is so thick that there's no wind erosion, or if there is, there's very little. There's no water erosion, no erosion from streams, glaciers, or or water waves because there is no water. And so there's very little erosion, right? The surface doesn't, probably doesn't change as much as it does on Earth. And the reason Venus is so hot is because of that runaway greenhouse gas effect. Right? So if the carbon can't go anywhere, it's just going to make the planet hotter. Now let's move on to Mars. All right, I don't know if you recall, about 2 weeks ago, we said that of the 5 terrestrial worlds, we said that the Moon and Mercury are geologically dead, but Venus, Earth, and Mars are geologically active, or at least have been much more geologically active more recently than the other worlds that I mentioned. So what do we know now about Martian geological activity? Well, we know that water once flowed on Mars. We know that Mars has certain kind of features that give evidence of geological activity. All right, so for example, Mars has these 4 shield volcanoes. One of them is the largest volcano in the solar system. On all of the different celestial bodies, Mars has the largest volcano. It also has a large canyon formed by plate tectonics. We can see on the surface that there are some regions that look like water once flowed, right? So typically we see like fluvial action in the form of like dried up riverbeds. There are also craters that have been modified by wind processes. So we know that Mars has we knew that Mars had an atmosphere, but that erosion actually occurs on Mars's surface. Right? So things can be eroded and weathered with time. And we also see that there's a large impact crater. So these are some of the main surface features on Mars. This link no longer works. I mean, I'll click on it just in case it's up and running, but last time I checked, they got rid of it. Yeah, I don't think that they have it anymore. Right, just like there's Google Earth, there used to be a Google Mars. I think if I just Google it. Google Mars. All right, I'll share this with you. It's not quite the same, but because it used to be like a 3D situation. Can you see both screens? You can see this, everyone?
Yes.
Thank you. So I'm going to zoom out a little bit here. I mean, if I zoom out too much, it just repeats itself over and over again. So let me maybe zoom in a little bit more. So this is what it looks like just in regular light. If we really zoom in, we see there's a lot of cratering, right? So there's not as much geological activity as there is on Earth. Right? We don't see this many craters still on Earth's surface. There's a big one. Here's like a dry riverbed. Right, you can sort of see how it looked like a river once flowed there. What else can we find on Mars' surface? Oh, look, there are some Martians over there just hanging out. I'm just kidding. Right, but you see, it's a lot of cratering. Let's maybe look at it in the infrared. Now it's much more defined. That's pretty nice. Oh, or I don't know what's going on there. And then there's elevation. Right. So if we see like the lighter it is in color, the higher up it is. And so these are, I believe this is Olympus Mons over here. It's a 21-kilometer volcano. Okay, in any case. Put that away. Let me share the slides again. Okay, we can all see this. Just making sure the slides are working.
Yeah.
Thank you. Okay. So how do we know that water once flowed on Mars? Well, again, we see these sort of like dried up riverbeds on Mars's surface. Right, something that was only formed, that only could have been formed by running water. And over time, like Mars's atmosphere has changed. But remember what we said, how like smaller planets cool off more quickly, and it's heat that drives geological activity. So if Mars cools down, we would expect not as much geological activity. Just from an atmospheric perspective, if the interior of the planet cools down so much that the liquid metal core solidifies, then you won't have much of a magnetic field to protect the planet from the solar wind. So in the early days of Mars's existence, right, it had this warm core. It was able to make a very strong magnetic field that protected its young atmosphere from the solar wind. The interior was warm, and so it outgassed a lot. Outgassing is a process when the gas is basically forced out from the interior to the surface. That's like when volcanoes erupt. We see a lot of that happening. And the fact that Mars had this thick atmosphere protected by a magnetic field allowed it to be warmer than it currently is. And that would have allowed for liquid water to flow freely on Mars's surface. So maybe once upon a time, Mars had an ocean. But fast forward to today, and that core has stopped convecting as much because it's colder. It has solidified quite a bit. And so there's less outgassing, or there's less gas coming from the interior to the surface. And there is a weaker magnetic field, which allowed the solar wind to sort of, strip away much of Mars's pre-existing atmosphere. There are some gases that remain. They can condense or they react with the surface, and as a result, Mars actually has it has polar ice caps at its north and south pole. And because it has a significantly thinner atmosphere, it retains much less heat, right, which is another key part to that. And so only for about the first 1.5 billion years of Mars's existence did it have water. And then at some point, probably around 3 billion years ago, it lost most of its atmosphere. It still has some, but it lost most of what it had because it cooled down. Okay, so to summarize, right, how do we know that water once flowed on Mars? There are dried up water features like riverbeds, craters, and floodplains, right? Only things that can be created by water. We know that Mars has ice today. We know that there's underground ice as well. So perhaps there are pockets, deep within Mars's interior where it's still hot, or or it's still the right temperature for liquid water, and maybe there is life on Mars living in that liquid water deep underneath the surface. Right, so why did Mars change? Well, as Mars cooled down, it lost its ability to produce a magnetic field, which was protecting its atmosphere. Without the atmosphere, there's not as much greenhouse gas effect, or greenhouse effect to keep the planet warm, and thus it became a lot colder. All right. How about the moon? How about Mercury? As I mentioned before, they are both geologically dead, right? They are no longer, they no longer exhibit any volcanic activity. They don't really exhibit tectonic activity, so on and so forth, right? Because they're all cold and shriveled up. They also can't really get rid of their surface blemishes. There are no erosion processes. So let's talk about the moon for a second. All right, the moon's got two main kinds of surface. One of them, and you can see in this image, is this sort of like, I want to say that this part looks a little bit smoother, the dark parts. Would you agree with that, folks? The dark parts look kind of smooth. And then the lighter part of the moon's surface looks a little bit more like heavily cratered, not as smooth. Right, so these are the two different parts of the moon's surface. There is the darker Maria and the lighter highlands, also called the Terrae. If anybody here speaks Spanish, then you might recognize the root of the word Maria is mar. Can somebody tell us what that means?
Can you repeat, like you said, Maria, right? It's like I speak Spanish, but I didn't hear the part like you said Mars.
So no, I said, so the root of that word is mar.
Oh, ocean, oceans.
Ocean, right? And the reason that the dark parts of the moon are called Maria is because early astronomers believed that they were oceans on the moon's surface, right? They kind of look like these smoothed out regions. So the Maria, being that they are smoothed out regions, suggests that there was once upon a time geological activity. Because if there was no geological activity, we would just expect a bunch of craters everywhere, covering every part of Mars' surface from that heavy bombardment era that occurred in the early solar system's formation. But these are smooth parts of the surface, which means that at some point there had to have been a lava flow on the surface that solidified over the existing crust. All right, so we're looking at ancient lava flows when we look at the dark part of Mars' surface. The lighter parts of the surface, are the highlands, or the terrae, which is Latin for land. It is lighter in color, it is very, very heavily cratered, and it is mountainous. Right? It is a mountainous part of the surface of the moon. Right? And we can infer that this part of the moon surface is older than the Maria, which is why we see more craters here. Right? If the Maria had been around on the moon's surface during the time of the early bombardment era, we would see craters in the Maria. In those ancient lava flows, we would see impact craters. But we don't. So highlands were around, right? They were already there, already formed during the heavy bombardment era. And then after the heavy bombardment era ended, there might have been a little bit of geological activity that pushed lava to the surface and smoothed out some of the blemishes. Now, part of the moon's surface is pulverized rock. Right? Pulverized rock is something that you would expect to see when a comet hits the surface and debris is sent flying, and then the debris settles. Right? There is no weather on the moon, so the material just stays there. Right? That dusty material just stays on the surface, and it just basically looks, it's like mud almost. And so here's a picture from the last manned mission to the moon in 1972. And on the ground, you can see boot prints. And also tracks from the rover, these tire tracks out there. And so here's a photograph of Buzz Aldrin from the Apollo 11 mission in 1969. This is when we first set foot on the moon. And we have Neil Armstrong saying, "One small step for man, one giant leap for mankind." And you know, it was not 8 years earlier that John F. Kennedy, you know, got on the news and said, "I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth." And lo and behold, we did just that. Moving on to Mercury. Right? Mercury, very similar to the moon, has heavily cratered and smooth regions. Those regions are likely, the smooth ones are likely ancient lava flows. But what we also see on the moon are these long, almost like, they're like wrinkles, right? Almost like, think of when you know, you have your hand in water for a long time and your hand looks like it sort of shrivels up, or maybe probably even better, like how a grape ultimately becomes a raisin if you let it dry, right? It just shrivels up. And when Mercury was very young, it cooled off very quickly and shriveled up. And this escarpment, or this tall cliff that cuts through the impact crater, indicates that the Mercury had to have shriveled up. So there had to have been some type of geological activity or tectonic movement that occurred after that period of heavy bombardment. Right? We know that this cliff had to have been formed after the period of heavy bombardment because the cliff cuts through the impact crater. If the cliff was there first and then the impact crater happened, it would have destroyed the cliff, but it did not. Right? So that escarpment that I pointed out before was the Roops Scarp. Discovery Roop Scarp, here it is. Right. There's a very large basin here from a very large impact that took place on Mercury's surface. You know, at some point, there had to have been an incredibly large asteroid or something that hit Mercury. And in the next slide, we're going to see, well, okay, here's the Caloris Basin. This colored region on the left, you can see right in the center there where that main impact happened. It's that yellow ring or orange ring with the blue dot in the middle. And you can see how it looks like all these lines are coming out from it. Well, when that impact crater occurred, it sent such a huge shock wave all the way through Mercury around the surface, that material bunched up on the other side. Like there are actual stress fractures, and you can see them here. Right, this is on the opposite side from that basin. A lot of energy just destroyed the surface over here. Lots of cracks. So was there ever geological activity? Yes, there was at some point for the moon and Mercury, but it was not long lasting, and it ceased a long time ago. Right, the evidence is, the ancient lava flows, but also the tectonic activity that we see on Mars from its shrinking, it's shriveling up. Okay, so to summarize our terrestrial worlds, Earth, very dynamic planet, lots of volcanism to this day, lots of plate tectonic movement to this day. Venus, the most recent geological activity that we have been able to determine was around 500 million years ago. Perhaps there's more geological activity to come, but maybe not. It does exhibit tectonic and volcanic features. And on Mercury and the moon, we know based on the number of impact craters on the surface that tectonic features ceased, or tectonic activity stopped a long time ago. Right, so the role of planetary size. We have these small terrestrial planets and large terrestrial planets. The small ones don't have enough heat to drive geological activity, but the large ones, which store more heat, they do drive geological activity. And so you see a lot of volcanoes and atmosphere and this and that on these terrestrial planets. And so here you can sort of see how the things that are smallest ceased that volcanic tectonic activity much earlier in their lifetimes. And here's the moon and Mercury. Mars, is it still, geologically active? Maybe, maybe not. Venus, maybe, maybe not. But the Earth is definitely still geologically active, right? And that's because it is of its size and its distance from the sun, right? It's at just the right distance that oceans could form. Right. So if you look here, here are the 5 worlds we were just talking about. And then there's this thing here called Io. This is not like an Apple operating system. This is a moon of the 5th planet from the sun, Jupiter. And before we talk about Jupiter's 4 Galilean moons, of which Io is one of them, we're going to talk a little bit about Jupiter. All right. Also on Earth, just to point out, this is a crater. This is the Manicouagan crater. It's the 5th largest known crater on Earth. It's located in Quebec, Canada. Formed sometime around 212 million years ago. And now it's this giant ice-covered lake. And it's about 70 kilometers across. This was taken by space shuttle astronauts, and you can sort of see the outer, showing the outer ring of the rock. All right, so let's talk about Jupiter and Jupiter's interior. What does it look like? What does it look like on the inside of a gas giant? Well, the first thing I'm going to point out is that this is actually a side-by-side image to scale of Jupiter's interior versus Earth's. Okay, Earth is much smaller than Jupiter is. And you can see there's the core, the mantle, the crust, and the atmosphere. And if you look at Jupiter's interior, Jupiter has a core also. I mean, it has different layers of hydrogen with different features, but at the core are rocks, metals, and hydrogen compounds. And the core alone is larger than Earth in its volume. So there's plenty of rock and metal in the outer solar system, but there is not as much hydrogen in the inner solar system as there is in the outer solar system. So that's why these more distant planets are much larger. So, you know, you can see that, you know, just the surface of Jupiter is this sort of like weird boundary between a gaseous hydrogen atmosphere and a liquid hydrogen ocean, pretty much. And there's all of this hydrogen on Jupiter's surface, but something funny happens to hydrogen when it's under a lot of pressure, right? It can change phases, right? Basically, like if you take a gas and you compress it, it can become a liquid. And if you compress it, it can become a solid. So metallic hydrogen is something that we don't really see on Earth. Hydrogen is under so much pressure that it starts to behave like a metal, even though hydrogen itself is not a metal. And I mean, if you just look at the size of this metal layer of like not solid metal, like a liquid metal layer, we know that on Earth, it's that small liquid core that gives Earth a magnetic field. Jupiter's got this huge layer of metallic hydrogen. And so we can imagine sort of what its magnetic field might look like. And I'll show you a picture in a moment. Right. For a quick comparison, here are the other Jovian interiors. Right. So Jupiter and Saturn, you've got like the similar gaseous hydrogen, liquid hydrogen, metallic hydrogen, and then a rocky metallic hydrogen compound core. This is color coded, so you can see that both Uranus and Neptune also have gaseous hydrogen around them, but then they've got a lot of just hydrogen compounds, right? So like methane, ammonia, water. And in the very, very innermost part of the core, you have rocks and metals. Plenty of rocks and metals. Right? But Uranus and Neptune are not as large as Jupiter and Saturn, and there's just not enough pressure to create the same amount of metallic hydrogen, or to create any metallic hydrogen. And so Uranus and Neptune don't have that layer. So now let's take a look at what Jupiter's magnetosphere looks like. Right? You can barely even see it in there. Right? Jupiter is like the size of a pinhead, almost, in this image. And the magnetic field around it is just enormous. So much so that, you know, those interior moons that it has are actually within reach of its magnetic field. And so anytime gases are emitted from its moons, it basically creates this ring of charged particles that orbit around Jupiter. And, you know, again, something that a lot of people don't realize is that Jupiter also has rings, just like Saturn does, but not as magnificent. Just like on Earth, we have auroras. We have the aurora borealis and the aurora australis. There are auroral regions on Jupiter's surface as well, at its north and south poles. So when we look at Jupiter, what we're seeing are the cloudy, the cloud tops above its gaseous hydrogen surface. And in this atmosphere, right, we have a lot of hydrogen compounds. Right? The further we get from the surface, the cooler it gets. Right? Basically, the closer you get to outer space from the surface, the lower the temperature is. And at different temperatures, different substances condense. and form clouds. So the different layers of clouds are different colors because they are made of different things. And so we can look at the clouds and say like, oh, you know, these really light beiges, that's from the ammonia in the atmosphere. And these sort of like darker reds, or these like lighter reds, that's the ammonium hydrosulfide. And then so like the gray and really dark reds, you know, that's the water that's condensating. Okay. Saturn's atmospheric layers are similar, but they are a little bit deeper in, right? And that's because Saturn is a colder planet because it's farther from the sun than Jupiter is. Right? And all of these planets, I mean, these are gas giants and they spin pretty quickly. Jupiter's rate of rotation is faster than Earth's, and it's a much larger planet. And that, coupled with the Coriolis effect, which is due to that rotation, gives rise to really extreme weather on these gas giants, very extreme weather. Many of us are probably familiar with the Great Red Spot on Jupiter. That is a storm. This storm itself is about the size of Earth. And this storm has been raging on, this hurricane has raged on for over 400 years. I mean, Galileo was alive, or this thing was around when Galileo was alive. All right, and then Saturn has even faster winds than Jupiter does, also lots of storms. Uranus has some storms. You can see its rings here. All right. And here's the Great Dark Spot on Neptune, which is also a very powerful storm. All right, so when we compared the planets, one of the first things that we made note of is that the outer Jovian planets, so Neptune and Uranus, are not the same color as Jupiter and Saturn are. So why is that? Right, well, those outer two planets have much more methane. Right? Methane is a hydrogen compound. It's a carbon atom that is combined with four hydrogen atoms to form CH4, methane gas. And methane actually reflects blue light but absorbs red light. So light, red, orange, yellow, that color light that's coming from the sun reaches those methane clouds and gets absorbed by the atmosphere. And then the blue light that hits the top of the atmosphere is just reflected back. So here's an interesting thought. If you were somehow able to get underneath those methane clouds, if it were possible to maybe get in a little boat and hang out on the surface of Neptune or Uranus, and you were looking at the sun, what color would the sun appear? Well, if all of the blues are being reflected and only the reds make it through, then the sun would appear very, very red. Very, very red. Anyway, moving on. And so what are our Jovian planets made of? Mostly hydrogen and helium gas. There are rocky and metallic interiors. There are rocks and metals. There are also lots of hydrogen compounds on Jupiter, and on Jupiter we see that there's this large layer of metallic hydrogen, and also on Saturn, but not on the outer two Jovian planets. So what is the weather like? The weather is crazy. Lots of clouds, lots of material condensing in the atmospheres of those planets. They all have very strong storms, lots of wind, much more powerful storms and winds than here on Earth. And now we're going to change the direction of the conversation and wrap up the next couple of slides. We're going to talk about moons. So first we have medium and large moons. What does it mean for a moon to be medium or large? Well, it has to have enough mass to it that it can actually pull itself into a spherical shape. Right? Typically, these moons have a lot of ice on them, and they tend to orbit the Jovian planets. It is very, I mean, the terrestrial planets have few moons, if any. Right? They also tend to orbit in a nearly circular path in the same direction as the planet's rotating. So for example, if you're looking at like a North Pole down view and you're seeing Jupiter rotate counterclockwise, then its moons would orbit around it counterclockwise as well. And so here are just some examples of moons that you'll find. And at the bottom are other objects for comparison. And so, you know, we look at like Mercury and the moon and Pluto, and we see that like Jupiter's moons are pretty much larger than you know, in this case, a planet, our own moon, and Pluto, which is a dwarf planet. You know, right? So there are plenty of interesting objects. And these are not even all of the moons. I mean, Jupiter has 79 moons, where the Earth has 1 moon, and Mars has 2. Venus doesn't have any moons. Mercury doesn't have any moons. All right, so then we got our small moons, and what you'll notice, one is that there are many more of them, but they're also not round. Right, so sometimes there are moons that orbit around a planet that don't have enough mass to pull themselves into a shape that is round. And so that's why these smaller ones tend to look like little potatoes floating around the planet. And these are not all the same size either. I mean, the Pandora is almost 4 times larger than Calypso, and Phoebe is, you know, just under 4 times larger than Pandora. Okay, so we're gonna, you know, now that there's some type of sense of like the size of moons and maybe the quantity. Right. Jupiter's moons are particularly special, specifically the 4 Galilean moons, Io, Europa, Ganymede, and Callisto. And that is because if you look at their size, they are particularly large. They are as large, if not larger, than some of the terrestrial planets. So Io, for example, is the most volcanically active body in the entire solar system. How is that possible, right? This is an object that is not, it's not a planet. Well, hold on. The reason it's so volcanically active is because of tidal activity between Io and Jupiter. How Jupiter's gravity is so intense that as Io moves around it and Io rotates, right, it basically elongates and compresses Io on 2 perpendicular axes, and that constant stretching and compression basically causes friction, which heats Io up from the inside, and that's just due to Jupiter's gravity. And so constantly has volcanic activity, lava being pushed to the surface. And then there's Europa. All right, Europa is a giant ball of ice for the most part, as far as we know. We don't really know much about its interior, but we believe that there is a very large subsurface ocean that's covered by all this ice. I mean, we know that there's a subsurface ocean, but we don't really know much about it other than that it exists. How do we know that? Because of all of these cracks. So for the same reason that Io is very volcanically active, right? That tidal heating from Jupiter, the water that's inside Europa is also pulled on, just like Earth's tides caused by the moon. Jupiter's causing these tides on Europa, which really push on that icy surface, crack the surface. So all of these cracks that we see here are the result of the subsurface ocean basically being pulled and compressed underneath the surface to fracture the ice. Right, so there's some tidal heating that happens, and these now large structures of ice brush past each other. They get hot, and that causes ice to expand, become a gas, and basically it spews out ice. It's like a cryovolcano. Right, we're going to look at a little bit more about cryovolcano volcanoes in like 2 or 3 slides. All right, so now let's move it. We're going to move on actually to Saturn's moons for a second. One of them is Titan. First, I don't remember who, but I believe somebody here is doing the Cassini-Huygens mission for their space mission assignment. Please tell me that this is going to work. There's like a 2-minute video from when the Huygens probe descended and landed on Titan's surface. What makes Titan very interesting is that it has an atmosphere, a pretty thick atmosphere at that. And let me share my screen here. Is this going to let me watch the video? Hold, please. Ah, there we go. Okay. Let me just make sure that this is showing the right stuff. Come on, it's not the right video. At least it's not the video I wanted to show. When in doubt, we'll go to YouTube. All right, so we'll look up the Huygens. Okay, here we go.
With Fundrise, the same kind of real estate investments that have powered the world's strongest portfolios for decades.
Begin Earth passing directly in between the Sun and Saturn, an opposition so perfect that it occurs maybe twice per millennium. Meanwhile, the Huygens probe, quietly entering the Saturnian system, is about to end its 7-year journey. As Huygens approaches, the inner planets cluster around the distant Sun. Saturn appears almost as large as Orion. A few moons are visible as white dots aligned with Saturn's rings, while Titan, its largest moon, is already well resolved. Huygens is destined for Titan, a mysterious world larger than the planet Mercury and shrouded by a thick brownish-orange atmosphere. The details of its surface have never been seen. Huygens' speed increases to near 6 kilometers per second, and Titan's disk quickly obscures our view of Saturn and its more intimate moons. As the probe enters Titan's atmosphere, the heat shield reduces the speed some 15-fold within a few minutes. The main parachute reduces the speed further. 15 minutes later, the smaller stabilizer chute allows a faster descent at first, but slows as Huygens enters the lower, denser parts of Titan's atmosphere. Huygens is approaching a dark valley between brighter, hilly regions. Beyond the hills to the left, 2 dark parallel lines appear, which are later discovered to be part of a vast system of dunes which surrounds the moon. At 21 kilometers altitude, the probe moves through a thin haze layer as seen on the horizon. The bright area near the center top is the glow of Titan's haze illuminated by the sun. A complicated system of drainage channels, some hundreds of meters wide and kilometers long, are seen cut into the hillside. These are probably the result of runoff from methane rain. Stereographic imagery reveals hills to the left to be perhaps a few hundred meters tall, while features in the valley are tens of meters in height. For most of the descent, the probe travels eastward above Titan's surface. However, below 7 kilometers altitude, the motion reverses into a backward westward motion. It reverses again at 1 kilometer altitude, and we move slowly southeastward. Hang on, as Huygens lands on Titan's surface near a water ice outcropping ridge. Another westward-looking view of the descent from 31 kilometers shows the area of Titan over which the probe has just flown. This affords us a good view of the drainage channels and apparent shoreline. More dark lowlands appear, and a rough pitted hillside to the left. Spectra of the surface suggest that the bright areas are water ice, and the darker areas are a type of hydrocarbon mixture that has never been produced in the laboratory. The small white dot in the lower center part of scene tracks our progress over Titan's surface. We see the reversal in direction at 7 kilometers altitude, and we fly over the ridge near where we will land. As we approach the surface, our perspective brings the topography to life. We see that although there are rivers and a shoreline, the basin is dry. Below, there are distinct signs of erosion which crafted the rugged ridgeline. Huygens sinks into one of these gullies. We experience a relatively soft landing on Titan's surface. The view from the surface reveals an amazingly Earth-like picture of a dry riverbed, with distant hills which are a few meters in height. Some seconds after impact, the shadow of Huygens' parachute drifts across the scene. The heat from the surface science lamp in the probe's skin vaporizes methane from Titan's surface, which is about 180 centigrade degrees below freezing. Near the probe, the ground is littered with water ice rocks and smaller pebbles, which could be made of water ice, or hydrocarbons, or some combination thereof. Although we now know more than ever about this mysterious world, many questions remain unanswered. Where is the vast reservoir of liquid methane necessary to replenish the atmosphere? Where and how often does it rain on Titan? How does the methane get recirculated into the atmosphere? What materials make up the surface? What processes create and shape the hills, dunes, and valleys?
My name is Scott Harris. Just listen.
All right, so that was a fun little view from the Jet Propulsion Laboratory, NASA, right, of that mission. And so whoever's doing the Huygens probe mission should probably watch that video again. Okay, so again, here's Titan. Very, very interesting moon. It's got an atmosphere. It's Earth-like underneath all that haze. Another one of Saturn's moons is Enceladus. which is interesting. It's got these icy volcanoes, again, cryovolcanism. You can see these tiger stripes right along the surface are regions where ice is emitted from volcanoes. And so basically we have, parts of the icy surface that move past each other and heats the ice underneath, which becomes a gaseous vaporized water. And it is believed that these icy particles are what make for Saturn's icy rings. Right? Now there's another moon out there called Mimas, M-I-M-A-S. Some of you might recognize this moon. Anybody? Remind you of anything? Come on, one person's got to say it. What does Mimas remind you of? Nobody? Gosh, you're all such disappointments.
I'll tell you what it reminds me of.
Too late. I already showed you. It's the
Oh,
Death
come on.
Star. You should have answered the first time I asked you 30 seconds ago. Right? It is the Death Star, right? The inspiration for the Death Star is this moon Mimas. Right. So rocky planets versus icy moons. What's the big difference? Well, the icy moons will melt at lower temperatures, right? And that's why, like Europa and Enceladus, even though they are basically these giant balls of ice, there's still geological activity on their interiors because they're made of ice. And so they melt at lower temperatures. And so just a little bit of tidal heating from Jupiter and Saturn causes them to melt and emit plumes of gas. Whereas on Earth, or rather for Earth's moon, or Titan, Saturn's moon, the tidal heating that happens is not enough to actually melt the rock. And so there isn't really as much geological activity. All right, so that's why only the large rocky planets, Earth, Venus, Mars at some point, have geological activity. Right? Again, the tidal heating can melt that internal ice. So let's just summarize in 2 more slides what we've learned, and then we are all set. So 1, the kind of moons that orbit Jovian planets tend to be moons of many sizes, right? We have big moons, small moons, medium-sized moons, and there is an exhibition of geological activity, but it really depends on the size. So like the smaller moons, not a lot of geological activity. They're not really large enough to hold on to heat that drives activity. But the bigger moons, lots of geological activity. Right? So why are those 4 Galilean moons of Jupiter very geologically active? It's because of tidal heating, right? As they orbit Jupiter, Jupiter's constantly pulling on them and stretching their insides and causing friction to heat them up from the inside out. Right? And so we end up with these very interesting types of activity. Right. So what about Titan? What about these other moons that are not around Jupiter? Well, Titan's got its own atmosphere, a moon with an atmosphere. Other icy moons like Enceladus have geological activity. We have cryovolcanism. So why is it that these moons of the larger Jovian planets sometimes have more geological activity than terrestrial planets like Mercury or Mars? Well, it's again due to that tidal heating, right? That Jupiter's really able to stretch the interiors out and cause them to heat up in a way that the interior planets aren't able to. Right? There is nothing that causes them to do that. So we don't really see that kind of geologic activity. And with that, folks, we are done. All right, so I'm gonna stop the screen share. All right, I'm gonna stop the recording.